All right, so today in AP Calculus we are looking at L'Hopital's rule, and this rule, what does it do, okay? What does L'Hopital's rule do for us? Well, L'Hopital's rule comes into play when we have limits, when we're working with limits. It actually uses derivatives to help us determine limits. Now, this is a question down here that you can write down if you want. We're going to work on this in a little bit. But this is something that we've seen before, and you've been able to evaluate this limit, right? But this is in, if you just plug this value in to see what is the function here at x equals 3, then you would get what? What would you get? If you plug 3 in here, you would get 0 divided by 0. Okay? Still frozen? How's that? Still frozen. Okay. How's that? You get 0 over 0. Right? All right. So L'Hopital's rule helps us to determine limits using derivatives when we have something called an indeterminate form. So let's just jot down those notes there real quick on that. So it helps us find limits for indeterminate forms, which are forms where you see you have 0 divided by 0, as we see down here. Other forms too, if we have like infinity divided by infinity, or 0 times infinity, etc. So things like this, when we run into big problems like this, we can often use L'Hopital's rule to help us determine this. Now, so it uses, L'Hopital uses the concept of the derivative to determine these limits. Uses derivatives to find limits. Now, we spent a lot of time early on in this course talking about how limits help us to find derivatives, right? And we kind of said that we can use limits to determine the derivative and all that sort of stuff. And so we've gone from limits to derivatives before, but now we're going to be going from derivatives to solve for limits. So we're not going to spend too much time on how we would determine this limit, before this rule. But if we had something where we plugged this in to evaluate it and it came up with 0 over 0, if we just plugged 3 in for the variable, then what would we do? Just really quickly, you guys remember how we would tackle this problem? In the past, what we would do is we would try to factor the top and factor the bottom if possible. And we would try to manipulate it in such a way that we didn't have 0 over 0. So what is this here? This is x minus 3 times x plus 1 over x minus 3. And so we would say, hey, you know what? When this is simplified, when it's all said and done, we actually have, this actually looks like the function x plus 1. We just have a gap at x equals 3, right? This represents a gap. And so we would say, even though it doesn't evaluate at x equals 3, we know that there's a limit, because it looks like a straight line, and so that straight line would come in like this, and there would be a limit, a y value limit there. So that's what we would do. Now, if you have a form 0 over 0, like that, if you plug the value in and you got 0 over 0, we're going to use L'Hopital's rule. Now, how do derivatives help us to find this? Let me just talk about that real quick. So we're going to go over to Desmos here, and you don't have to jot this down just yet, but I'm going to light up here this exact question. So here's the numerator, here's the denominator. Does everyone see that? So if we look at this, and we're talking about where x approaches 3, so at this x value, what is the limit of this division? Okay. Now, again, I separated this into the two functions. Okay. But how do derivatives help us to determine what this answer is? And so if we go back here, what would the derivative be? Or what would the limit be, sorry? This limit is, sorry? 4. Yeah, the limit would be 4. Okay, once we manipulated this, it plugged their value of 3 in, because x minus 3 would go with x minus 3, and then x plus 1, so 3 plus 1 would be 4. So the hint is that L'Hopital's rule deals with these two functions separately, the numerator function and the denominator function. And so let's take a look at this. I'm not going to give it to you right now, but I want you to know that when we look at this point and we try and find out what the limit would be of this function divided by this function, the concept of L'Hopital's rule is based on local linearity. Okay, now do you remember what local linearity means? As I zoom in here, can someone tell me what is local linearity, that property of functions? First of all, what does local mean? Okay, local, yeah, in not exactly one isolated spot, but in a spot that's immediately surrounding a certain point, right? So local means right around. Now, linearity, that's the root of that word is linear, right? So if you recall, and we've done some study on this already, but as you zoom in, okay, the tangent ends up running alongside and actually is almost identical to a function if you zoom in far enough. So look at this right here. You see these? That looks like two straight lines, doesn't it? I've zoomed in incredibly right here, and these look like two straight lines, but clearly one is a straight line, but one is a parabola. So this is the concept, local linearity. And what this helps us to determine is that, look at, if I find the derivative of this red function right here, the derivative, at this point, x equals 3, then it's going to be a straight line that virtually mimics the function there. You see that? It's going to be a straight line that's virtually right on top. And the same here. Obviously, this is a straight line, so the derivative, the slope of the tangent, will be mapped right on there. So what we see is something interesting. If we take a look at it, I'm going to clip this into the notes here. Whoa, I don't want that. That's from science class. If I clip this into the notes here, and we'll bring this over so I can kind of work on this a little bit. What we're going to find is that, so derivatives are the slopes of the tangent lines, right? So watch this. What would be if we took, well, let's take one square, one of these little squares, okay, as a run. Let's take a look at what is the rise of the one function on top compared to the rise of the other function. So the red function is this one on top. And so what is the slope here of this? Let's assume it's a straight line. What do we have? 1, 2, 3, 4, and over 1. So we have a rise of 4 here as a run of 1. What about this one? Well, we know that this is a slope of up 1 over 1. Right? So the slope here, the slope of this, if it was a line, would be pretty close to 4 over 1. Everybody see that? The slope of this one, if it was a line, and it is a line, is 1 over 1. Okay? Now, that's interesting. What's further interesting about this is that if we take a look at the slope, what's the slope? Okay, so the slope is rise over run. So let's use just over here. Rise over run is the slope, right? And so if we took a look at the derivative of the top and the derivative of the bottom, okay, of the top function here and then the bottom function, the rise we said here of the top function was 4 over 1. And the derivative over here was 1 over 1. So that's the same as 4 over 1 or 4. Now that's interesting because the rise really is a change in y, isn't it? And the run is really a change in x, or to put it another way, a small increase in y over a very small increase in x. You see that? So we know that slope is virtually the same, if it's a straight line, it's the same as the derivative. So look at this. We have the derivative of the top function basically divided by the derivative of the bottom function equaling the same as this limit here. Okay? So if we have an indeterminate form of 0 over 0, taking the concept of local linearity, if you have the same run and you compare the ratio of the rises with the same run or the slopes of the tangent lines there, then the ratio of the tangent lines is going to be equal to what the limit is. These are going to be equal. And so that, in essence, is L'Hopital's rule. Using local linearity, L'Hopital's rule says this. I'll take a moment to write this out. And this is sort of like, what do they call it? First form. This is like the most basic first form, okay? If you have a limit of a function divided by another function, f of x over g of x, and you want to find that limit as x approaches a, then what you simply do is you find out what is the expression of the slope of the tangent lines, and you evaluate the ratio of those at point A, and you get the limit. Okay, so take a moment to write that out. Let me know if you have any questions. All right, so a couple questions were, what if the run was different? Okay, well, we're still examining the slope. So because the runs are the same here, I just kind of crossed these out here. So really, it's just the difference in y over the difference in y, right? So it's 4 over 1. If this run was different over here, then it would still be the slope of the one line, okay, or the slope of the tangent at, in that local area there, divided by the slope of the other tangent. Evaluated, really, it's got to be evaluated at the point where they meet there too. So that's the point where it makes them 0 over 0. But that's in essence L'Hopital's rule. So if you have, this is for 0 over 0 indeterminate form. Okay. All right. And the other question was, what was your other question?
Is that rule still work?
Oh, of second derivative. Okay. Well, what's going to happen is we're going to do some examples later where we're going to take the derivative of the top, the derivative of the bottom. We're going to plug in a, and it's still going to give us 0 over 0. Or it's not going to help us at all. So yes, then what you do is you just do it again. Because if you think about it, why is this the original function and why is this not represented as a derivative? Then this would be the second derivative, wouldn't it? So the rule still, you can take any function, wherever it is in the continuum, and take the derivative of it. Okay, so yeah, so you can take the second derivative. And we'll do questions like that where you'll have to take second derivative because the first derivative kind of won't be enough. And those examples will be coming up. So just a couple other notes here too on L'Hopital's rule. So again, take the derivative of the top divided by the derivative of the bottom, evaluate it at this a that makes this 0 over 0. And if you have to do that again, take another derivative and another derivative until you get a concrete constant value there. Then you keep doing that. So for indeterminate forms, okay, I just have to make a note here. For non-indeterminate forms, it's not, this doesn't hold true because we have no control over these constants. These constants can vary quite a bit. And as you see here, I just kind of did a random one, or is this the same? No, that's a different one, sorry. I just did a random one here just for an example. And of course, as you plug 3 in, if this is not an indeterminate form, then this is the limit that you would get. But if you took the derivative of the top and the bottom, you would get this, which is slightly different. So it doesn't quite work. And if you think about it, this would be, I don't know if I have this on Desmos. Let me just see for 1 second. Okay, well, I have another pair. But let's say we have something like this and then something like this, okay? And they don't line up. They don't actually cross each other. You know what I mean? They don't intersect. And so these constants, are going to alter things just a little bit because when you evaluate this, if this was a 6, the derivative would be the same. If this was a negative 100, the derivative would be the same. So, obviously that's going to affect the numbers we get here and here. So it only counts. It only helps us if it's an indeterminate form. The one other thing that I would mention though is this: what if you have infinity divided by infinity? Okay, if you have something like that, like so for example, if you plug your value in and you get infinity on the top and you get infinity on the bottom, then consider this, that infinity is really just, it's the same as 1 over 0, right? And so if you have something in terms of infinity here, if you took this one and you put, moved it up here and made it 1 over infinity, that would equal to 0. So something 1 over something very large, that's this one down here, and then something 1 over very large, then you would get 0 over 0. So again, I hadn't really planned to do this in this lesson, but anyways, if I had f of x over g of x, and this gave me infinity over infinity, then what I could do is I could do 1 over g of x on top and divided by 1 over f of x on the bottom, and then really these are the same, right? Like if you flip and multiply, you'll get 1 over g of x, and so then you get 0 over 0, and then you can do L'Hopital's rule on this. Okay? I'm just going to take a second just to double check that, okay? All right, so the example is, let's do this example, as x approaches infinity of x over x squared, okay? So if you plug in, x approaches infinity, well, x is going to get incredibly large and x squared is going to get incredibly large, so really this is infinity over infinity, right? Which doesn't make any sense. However, if you change this so that it looks like this, and you go 1 over x squared over 1 over x, that's the same. Algebraically, that's the exact same as above. And then what happens as x approaches infinity, 1 over x squared, that approaches 0. And 1 over x, that approaches 0. So that's a different form. It's the same function, but written a different way. And you can apply L'Hopital's rule to this one, because it ends up to be 0 over 0 when you plug your value in, sort of thing. Okay? That's kind of another level one, but if you just think about L'Hopital's rule in indeterminate form of 0 over 0, that's what your basic questions are going to be. Okay? So there's L'Hopital's rule right here, and that's what we're going to work with. We'll do some examples for that. Okay?